Okay, we're revisiting the Archaeopteryx from the last lesson. And so the data is the same, but now we're going to head and ask you a few questions. So I do have the answers already filled in here, but basically, how did I get the equation in the line? So what I do is I type this data into a statlet. So I've got a two quantitative variables statlet. Let me just go ahead and make sure you know which one I'm talking about. So if you go to statlet.com, this one that says two quantitative variables should look like two rows there. That is what we use for putting in the data. So this is the tab I already set up, and I put in the femur data and the humerus data. And you can just hit begin analysis, and it shows you the scatter plot, which we had before. And you can actually, that's the same scatter plot I have there. And then if you scroll down, there are a couple buttons you can hit. So you can calculate your correlation. So you can see this is actually a very strong fit. And you can calculate the least squares line. So you'll definitely want to hit that calculate least squares line. And here's the equation. It shows you how many data points you have, something called the standard deviation of residuals, which you won't have to deal with, and r squared. And remember, we already had r up here. So if you go ahead and type this bit in, so here's your equation from the statlet. It's when you put it in words, so I'm going to kind of paste it in here just so you can see what the equation looks like. All right. So that's the equation straight out of the statlet. Ideally, you should actually write the equation so that it is in context. So what do I mean? Well, instead of going y hat, I'd say, oh, the predicted humerus length, because that's the y, equals, and then there's your value. I kind of rounded it a little bit. Plus there's the slope, and then the x, well, the x is the femur length. Now it does ask what is the correlation coefficient, and if I go back to the statlet, this is the correlation coefficient r, 0.9941. So there you go. What is the y-intercept and what does it mean? So the y-intercept is the constant. If you look at statlet, I know you're used to y equals mx plus b, but in stats, they tend to like to have x's in increasing power. So they actually do the intercept first, and then they do the slope in x. So here the intercept is negative 3.66. So what that means is if I put in 0 for the femur length, I expect the humerus to actually be negative 3.66 centimeters. Now that doesn't make a lot of sense, but that's just how the equation's working out. I suspect as it gets very small, maybe the femur and the humerus are probably closer to the same size for very small critters. All right. Then it asks you what is the slope. The slope is this value right here in front of the femur length, 1.197. So that means every time I increase this thing by 1 unit, so 1 centimeter, then I expect the humerus length to go up by 1.197 centimeters. So that's a typical way that we interpret it. Now to do a prediction, you're going to take this equation and you're going to put in the femur length. So what is the predicted humerus length for a femur measuring 45 centimeters? Well, we put 45 in the equation. So if I go 1.197 times 45 and subtract this 3.66, I get 50.21. The actual humerus length is 56 centimeters. What is the residual? So the residual is like the amount either over or under predicted. And if we put in the actual here, you just take the actual minus the predicted. It's always in this order. The actual is 56 minus what we predicted, and I'm going to just do 50.2, is 5.8 centimeters. Now, one thing we might ask you is, did we over or under predict? Well, our prediction was 50.2, but the actual was 56, so we under predicted. So you might see this question every once in a while. It's not right here on this assignment, but you should be able to figure out when you're doing this calculation if there was an over or under prediction. Now, it says what percent of the variability in humerus length is explained by the variability in femur length? So you can take this r up here that we had at the very top, the correlation coefficient, and square it. And whatever that is, and I should go ahead and change this to percent here. So it's 98.8% of the variability in humerus length is explained by changes in the femur. All right, so most of the variability in that is explained by the variability in the femur. Would you be uncomfortable making a prediction of the femur is 20 centimeters? Well, our data, our lowest value was 38 to 74. So we're going off graph, so we're no longer sure. In fact, you can kind of guess that it probably doesn't stay linear all the way to 0 because we're predicting a negative humerus length here. So something's broken there. So when you start getting outside of the range, you may be getting outside of what the bones are allowed to be. So it would be, this is called extrapolating, whether you're going lower than the set of data or higher, as long as you're outside of the range of the original dots. So if you predict before or after, then you are extrapolating, and we don't like to extrapolate. All right, going on to the Merlins that we visited last time. I also created a statlet for that. And here's the data for the breeding pairs and the percent of males returning. And then I hit begin analysis. So looking here, I can say calculate the correlation. And while I'm at it, I might as well do the least squares regression line because I need the equation. So here's the equation. It says equation, so that's kind of handy. Oh, and they do have your r squared calculated there too. So you don't actually have to square the r. You can actually, if you have the data, whoops, sorry about that. If you have the data, like the x and y values, you can actually have it report r squared when it gives you the equation. So you can see it's right there. So what is a correlation coefficient? Well, that was earlier, up higher, negative 0.7943, and there it is. What's the y-intercept? The y-intercept is, this first piece is the y-intercept, all right? And then what does it mean? Well, if we had 0 breeding pairs, we would expect about 157% of the males to return. A lot of times y-intercepts don't make sense. So it's like, well, gosh, 157% of 0 is 0. I guess that would work, but it's kind of weird. All right. What is the slope and what does it mean? So if I go ahead and we'll go here. So the slope has to do with this number right there. So I had kind of rounded this big giant number that I had over there. So every time this goes up by 1, and since x is the number of breeding pairs, so for every extra breeding pair, we expect 2.99% less of the males returning. Predict the number of males returning if there were 35 breeding pairs. So all I have to do is take 35 and put it into the equation right there. So we're going to do so right here, I just put in 35, right? And here, let me undo that. I didn't like that. Come on. Here we go. So I put the 35 in there. You see the breeding pairs, and it comes down here. So 35 times 2.99, basically almost 3. And then subtract that from 157.68, and we get 53.03%. So if the actual percent of males returning was 55%, what is the residual? So we said, oh, the actual is 55%. We predicted 53%. So we actually, the residual is 1.97%. So we under-predicted by 1.97%. How do I know we under-predicted? Because our prediction is under the actual. And then you can see here, see how that says 0.6309 is the next one for number 15. It says interpret R squared. R squared tells us how much of the variability in our y is explained by our variability in the x. So by the, I should say variability in the number of breeding pairs. And that is pretty much it. So that is your check for understanding. And hope if you have any questions, you're always welcome to bug me.